All right, folks, everybody, welcome to CS10 Lecture 22, Limits of Computing. Woo! All right, you still got some love. I love it. That's great. The news of the day is that researchers have looked at Facebook's connected social graph. How many of you know of the phrase 6 degrees of separation? Those of you who are not raising your hands, what that means is there's a philosophy that you are no more than 6 people that you know away from anybody in the world. So if you were, even casually, like somebody you just passed on the street whose name you know or face you know, as long as you know them, we consider that a connection in the 6 degrees of separation. Thumbs up on that one? Yes. Great. So what that means is, it's kind of cool. It means the world is small, right? It means the world is really small. It means that at most 6 connections between you and everyone. Even somebody who lives as a hermit knows their mailman, and that mailman knows a lot of people, and that, right? So it's 6 to you, so that's kind of cool. And it turns out they did some research on the Facebook social graph and found that it really is 4.74 degrees of separation, if you consider a friend. And even that's a higher bar than just being an acquaintance of your mailman, right? So 4.74, the number of friends separating any 2 people in the world, this is obviously not everyone in the world, it's the Facebook graph, but it's still pretty cool that they say you can get to everybody in the world in fewer than 6, now 474. That's kind of cool stuff. All right? So what we're doing is, today is the limits of computing. We realized as we were building this course that people may think that non-majors, people who are coming to this new, never seen this computing stuff before, may think that computers are perfect. And they can do things infinitely fast, they have infinite storage, and hopefully you're reading about blown to bits and you realize things aren't infinitely fast, we don't have infinite storage, we have near infinite storage, and it's near infinitely fast, but it's not. We also can't represent things perfectly, so there's a limit to how close we can represent numbers, okay, that as well. Today, the topic is limits. What are the limits of not only what you can represent and store, but also what you can compute? Is there a limit to what you can compute and not? We've already talked about you can't compute the solution, a strong solution to Go. We've already talked about that, okay? And people try to compute, the April Fool's joke was computing a perfect solution to chess, which is obviously too big also. So this topic is called, this is in the field of complexity theory, which is under the subfield in CS of theory. So just giving you a context of all the possible places that we've carved up computer science to kind of make some manageable sense of it all. It's in the family of theory, okay? So in the family of what things are hard for a computer, we have different ranges. Those range from problems that are tractable with efficient solutions in reasonable time. That's what we like. We like things that we can do. They're tractable. I'll explain what tractable means. Efficient solutions, that means we can do them. That's nice. It's not wasting time or wasting space or wasting data. In reasonable time. Reasonable, just whatever reasonable means for that time. Usually it means compute it in real time or compute it in a day if it's a bigger problem, or a week. But a year probably is too much computing time, unless it's really, really important. If you said, Dan, compute for a year and you can cure cancer, I'll take that year. But if it's like, compute the solution to the next move and tic-tac-toe, I'll give you it in a year, a little bit not so reasonable. So it kind of depends what you care about. What intractable means, some problems are intractable. We'll explain what that is. Are solvable approximately, but not optimally. That means we can guess what the best solution is, but I can't give you the exact answer. But I can give you a pretty good first guess. Okay? Have no known efficient solution. So that means not only can I not do it approximately, I can't even get close to it, and are not solvable at all. And the parts that are not solvable at all is the part that's going to really stretch your brain. Hopefully your brain stretched a little bit at recursion. For many of you, that was brand new and that was hard. Many of your brains stretched also when I talked about higher order functions. That was new for many of you as well. Wait, functions can be dated to in first class? Yes, indeed they can. And what we're talking about here is probably the third thing that's going to stretch your brain in this class, which is problems that cannot actually be solved. And that seems like, well, Go can't be solved. No, it could be if you give it enough time. I'm talking about something that can't even be solved ever. And that's a really hard thing to wrap your head around. So hopefully we'll have enough time for that. And definitely be using the live feedback for whether you're getting it or not. So the best case is tractable with efficient solutions in a reasonable amount of time. That's like almost everything we've given you so far is in that category. Sorting a list, or removing duplicates, or making something that kind of has, what was our midterm exam? A swirly thing that emulates the motion of the moon around the Earth, which itself is going around the sun. All those things, efficient, reasonable, tractable. Okay? So we came up with 6 categories of orders of growth. You may recall that. This is a review from constant, the best case, to logarithmic, still pretty good, to linear, I'll live with, to now things are getting harder, quadratic and cubic, still better than the last guy, exponential. Okay? That's the kind of ranked order of those guys. Order of growth, things that are tractable with efficient solutions in reasonable time are those that are polynomial. Polynomial. That's the key thing. For this slide, the whole key word is polynomial. What does that mean for the 6 things that we have? Which of these are polynomial? Quadratic, cubic, polynomial. Linear, right? Constant, logarithmic, also polynomial. Okay? So it means that everything but exponential, we're going to consider order of growth polynomial, tractable with a reasonable amount of time. Okay? Those things we've shown you, quadratic and cubic. Not all polynomials, but the guys that are there. With n to the squared and n cubed, all those things are reasonable. With big N, the kind of n we usually have, I can still solve those guys. Okay? So here's examples. On the right, you're going to see examples of things we do. Searching. We saw that one, searching for an automated collection. What's searching? Best case. Worst case of searching is what? Linear, right? I have to go through every single person. It's like, do you have my keys? No. Do you have my keys? No. Do you have my keys? Keep going through each person. Worst case, I hear it on the last person. Okay? So that's that. The best case of searching. Well, we saw best case of logarithmic. How? Binary search, right? Okay, if I'm looking for a number from 1 to 100, and I guess 50. Remember, we saw this before. Then 25. Right? Then 37. I'm cutting it by half every time. That's going to be logarithmic. What's the best case? I have an array. I have a list of it, and I say, is it here? Bloop, and I look for it immediately. So the best case is actually constant for that, for searching. Okay? Sorting a collection. You're going to see in other classes that sorting collection is at worst case typically n squared or quadratic. And if you're really good about it and really smart about it, you can get it to the level of, it's called n times log of n. So it's kind of like the product of linear and logarithmic. But we haven't seen that categorization here. But n log n is still within the quadratic. It's still smaller than quadratic but bigger than linear, so we would call that quadratic. Okay, n log n. So still quadratic for doing this searching thing. There's an optimization, by the way. You'll see this cool optimization called radix sort, where you can actually do things in a linear way, and we can talk about that in a best case. But that's average case. Worst case, it's still not so good. But all these things you'll learn later. That little thing I just said, don't worry about that one. That's for later that you'll learn. Finding two numbers in a collection are the same. That's like the two birthday problem. We saw that as what? Do you remember that one? Finding if two numbers in a collection are the same. I have a list of numbers. I don't know what they are in advance. And I haven't seen them. I can't pre-process them. You just handed me a list of n. N might be 1,000,000. And I find out if anybody the same. Think of the Twitter problem. And they say, I wonder if two of our user IDs are the same. We messed up somehow giving out these internal user IDs. Are they the same? And they have them all in a big collection that are not sorted, not anything. How long would it take them? And n could be big. N could be like a lot of people, 100 million people. So how hard would that be? N squared, right? You're comparing everybody against everybody else, right? And that might be cool. You might say, well, we could be more clever than that, which is what we do is we just sort it. And we saw, again, a moment ago I told you that sorting could be n log n, and then you just linearly walk through it and see if anybody's the same as the neighbor. So you can do it a little bit better than n squared, but for now it's quadratic, okay? These problems, this is important, and my thing is blocking a little in the corner. These problems are called being in P, in the set of polynomial problems. So from now on, if I say the phrase in P, it means in the set of problems that are like this: tractable, reasonable, and polynomial time. Okay? Intractable problems. Problems that are just too big to get your hands around. Okay? So they can be solved. We know of a solution. I have an algorithm, but I can't do it efficiently. And I can't do it efficiently means I can't do it in a reasonable amount of time. So these include all the exponential problems. We saw the tractable ones that are the top 5. Exponential is the one below. But there actually are things between cubic and exponential, like n to the 4th, n to the 5th, n to the 6th. Still polynomial, but the exponent of the polynomial is too big. So here's n to the 10th. Come on, if you give n 1,000,000, n to the 10th is way too big. So that would count as an intractable, okay? Even though it's still polynomial, an intractable but polynomial, and that kind of overlap, all right? We can solve it for small n and 1, n2, but I can't solve for n, n a million. So here's an interesting example. What if I have a problem that requires, like here's this big tree, this graphical tree on the right, and it requires some work to be done. And by the way, n is the number of levels I have of this tree. So here I have 1, 2, like 3 levels. Maybe this is like an ancestry tree, okay? And imagine the work you're doing is on the leaves, the guy in the bottom of that tree. Well, what's the number of circles, or maybe children on the ancestry tree, if I go down, if I always split and always have 2 kids or something, okay? Maybe looking at the woman's line, and the woman always has 2 girls, okay? Keep doing this. How many kids are at level n? I double every time. Well, n is 1, number of kids is 2. N is 2, number of kids is 4. N is 3, as in this picture, number of kids is 8. It is 2 to the n. Oh, man. 2 to the n is now exponential. So that kind of a problem, I can already tell you that that problem is intractable. For large n, I can't go 100 levels down and say how many kids do I have. Okay? I mean, I can say 2 to the 100, but I can't do anything. I can't compute something for every kid, is the point. Okay? So intractable means too big to solve. It's not that earlier 5 case. It's like a polynomial with a big exponent, or it's exponential, which is it's 2 to the n, or it's some constant to the n, which is typically going to be bigger than n to the big number. N to the 10 gets dwarfed by 2 to the n if I go big up. It looks like, oh no, n to the 10th, come on. That's, n to the 10th, that's huge. But 2 to the n grows faster than that. You're going to see that. Okay? All right? So far, this is still a little bit review, so it's not too bad. Now, here's the cool thing. I'm going to actually stop the clicky thing because I want to ask you a clicker question right after this guy. Solvable approximately, but unoptimally in reasonable time. So that's interesting. That is a whole new area of theory research, which is to go back to the problems that you knew were intractable and tell me, can you do something reasonable? It might not be perfect, but it's reasonable. For example, driving a car so that it never deviates even a millimeter from the perfect center of the line of each of that lane, okay? Maybe that's intractable for the number of things, for a number of feet or something you're going to be driving, okay? But what if I expand that from being the perfect center to, hey, just don't go outside and cross lanes, right? Maybe that's now solvable in real time, and in fact, it is. They now have systems, Google has demo systems where they have a car driving down the street. If they only clung to the theoretical computer science model of, nope, you have to be perfect. You have to give me the exact perfect solution. Like, no, the world is soft. The world is squishy. I don't have to toe the exact center line. I can move a little bit as long as I don't cross over and hit somebody, right? So you often have real cases where a reasonable solution is going to give you good enough answers, okay? And most of life is like that. Meaning, another way to say that is, the only people that really care about the optimal perfect solution are the theoreticians. Because most of us live in a real world that says, look, I'm not going to give you the optimal stock choice options, but something's going to make you money, it's pretty good. You live with that, right? The world, you live with those kind of things. So for almost every case, you're happy with an approximation algorithm that gets you 99% of the way there. For almost everything you have in life, okay? If you can, solve it in real time. If it buys you, I can do it real time or faster versus waiting a million years to solve, okay? So this is important. Like, for example, the knapsack problem, one of the most famous theoretical computer science problems, which is the following. You have a backpack with a weight limit. Here, this backpack is 15 kilograms. There are boxes and weights and values associated with them. So you basically are going to be a robber and break into Tiffany's. And Tiffany has a whole stack of boxes. This box says it's, what's the number? $4, kind of a poor man's Tiffany's, for, maybe it's a candy store, 12, but it weighs 12 kilograms. And this one says $2, but weighs 1 kilogram. And you keep doing this, right? There's always a weight and a value associated with each of these boxes. But there's like 100 of these boxes. So it's not like there's only one box. There's a lot of these boxes. It's just the characteristic box for each of their category, okay? The question is, which boxes should you bring if you know that the moment you hit 15 kilograms, the bottom is going to rip out of your backpack and you'll lose everything? You ever had this where you have a bag of, in the olden days we used to have brown bag, and you know that if the bottom gets a little wet, if you have a lot of weight, it'll break through the brown bag, but you can actually still hold a little bit. They can hold chips in a wet bottom bag. Okay, nobody ever bought clothes. Okay, nobody ever bought things in a wet bottom paper bag. But for those of you who ever bought paper bag groceries that the bottom got wet, it can hold a finite amount of weight like chips, but it can't hold like oranges or big milk. You can't hold 2 gallons of milk in a wet bottom paper bag, okay? Same idea here, okay? So what do you take? You could say, well, take all the greens until that fills up and then take some silvers and take some blues, but what do you take to be optimal? Which means optimal means exactly the most you could ever take if I let you make out every combination, okay? So now let's actually go and do that together. So what's interesting here, stay with me for a moment, is there are those problems that have actually no known efficient solution, okay? So that means there's no way. By the way, this isn't talking about approximation or not. This means that this is kind of the intractable space. This isn't the same thing as intractable. It is, to get the exact answer, there's no known efficient solution. And here's an example of that. I'd like to do examples first and then get to the details. The subset sum problem. Look at those numbers. Everybody see those numbers? Hopefully I don't have to zoom in for that one. Are there any handful of these numbers that if you add them together, they get 0? Yeah, 15 on one side and then minus 2, minus 3, minus 10. Excellent, okay? If I gave you a large set of these numbers, this has no known perfect solution. Efficient means you have to get the exact answer right. It can't just be close to 0. It has to be exactly 0. So approximation, if I need to get exactly 0 to make something work out, approximation is not going to get better. I can't get 0.001. It has to be exactly right for this problem. So this one doesn't allow for the approximation one. And this has no known efficient solution. You have no way of doing this. This is intractable. There's no known way of doing this. Now, here's a really interesting part. This is the point where this might start to make your brain hurt. Ready? Stay with me. There's a whole category of problems like this, okay, that are really hard. You can imagine. I can throw you a lot of these things, okay, that are really hard. Okay. One of the really powerful ideas, one of the most powerful ideas, I would say one of the top ideas in theoretical computer science is that you can take one problem and mask it, like in Halloween, mask it like another problem. And what that means is, at the core, if I solve that problem, I'd also solve this problem. Because it's like they're the same. It's like they're the same. I can take one problem and reduce it down to another problem. Okay? That reduction is so cool. Sometimes that reduction is complicated, but hopefully it's polynomial. How to take one problem and translate to the other is not, you can even do some work to make the translation, but you can still do it in a polynomial amount of time, a tractable amount of time. That's the reduction. So, here's what's really cool, okay? A problem P, this is the part where your brain might start to start. Ready, go. A problem P is hard. Hard means it's difficult. It's like the hardest thing you have in a set of problems. For a class C, for a kind of class of problems, if every element in that class can be reduced to that hardest problem. What that says is, if I crack the nut and solve that hard problem, I solve every problem in that class. Isn't that amazing? Okay. So, that's really powerful. There's 3 hard ideas on this slide. One is, there's a class of problems that are really tough to solve, okay? Idea A is that there's the idea of hardness, which is a couple of those problems are as hard as the whole thing. And what that means is, not only are they as hard as the whole thing, you can always rank order how hard things are to how easy they are. What this means in theoretical computer science is that if I find a solution to those guys, then every single person has their solution done. That's awesome, okay? It's like, here's a really bad example, but it's kind of a stretch. A whole new group of new houses come up. A whole group of new houses come up. And there's all these 75 new houses. Everyone is trying to find a good person to clean their carpets. And they're all trying it. But the moment one person finds an awesome carpet cleaner who charges good rates and does a good job, they all can use it, right? They can all get that solution benefit by having one person found the key solution. You kind of get it? So you all get to benefit. For one person found a solution, you all benefit. What we're saying in this theoretical sense is there is a set of those people that are the hardest ones. Those might be the hardest carpets to clean. Can you think about that? Because they have angles and that. There's no house that's more hard to clean than those ones with all the shuttles and angles and underneath stuff. But if you can find somebody who can clean those hardest houses, then everybody's house, which is easier than those to clean, can get this stuff cleaned. You get it? The opposite wouldn't work, right? You might find a good cleaning person for an easy house, but they might not have a shampoo system that would work around the corners and angles of the hardest house. Does that kind of make sense a little bit in the translation? But if you can clean the hardest house, you can clean everybody's house. Yeah? That was my analogy that tried to work. I stretched that one. Now, so that's this hard idea in the slide, step A. Hard idea in the slide, step B, is the following. Some of these guys, here's a solution. I propose a solution. The question is, can I verify that the solution put out by this thing can be verified, meaning I verify that's correct in polynomial time. You guys know what polynomial time means? It means not exponential, right? Can I verify that solution in polynomial time? Okay? Okay. This is still hard part B. If you can verify it in polynomial time, we call this being in NP. NP doesn't mean not polynomial. NP in your mind just means it is verifiable in polynomial time. Okay? So here's a solution. For example, ready? The subset sum problem. I'm telling you that you cannot come up with an algorithm that for any set of numbers, you come up with the answer, the subset of that. But here's a question. If I would randomly come up with a solution, right? How about the set of those 4 things? Someone yelled out, I have 4 candidate cases. These 4 numbers will add to the thing. Can I verify that in polynomial time? The student gives me an answer. Can I verify that in polynomial time? Yes. I just add them all together and I see if I get to 0. Right? So that was a proposed answer to this. Can I verify any answer polynomial time? Here in this case I say yes to that because that was linear. I just add them all up. The worst case is she says every number and I have to add every number up. That's still linear. Right? Linear means to do one thing for everything, every item. So the solution is, can I verify it in polynomial time? That's called being in NP. Hard thing number 3 on this slide, last piece. If you are in NP, which means verifiable in polynomial time, like we just saw for the student's answer, and you're NP hard, which means you're the hardest class of this no known efficient solution group. If you are, then you're in this exalted membership of a group called being NP complete. So you have to have 2 things. You have to be in NP, which means verifiable in polynomial time, like the student solution was. We just did that. And you have to be the hardest class of these no known efficient solution cases, like subset sum. And in fact, subset sum is both in NP, which means I can verify in polynomial time. I'll say it over and over. It is NP hard. It is that group of problems that it's the hardest kind of carpets to clean. And so therefore, subset sum is NP complete because it has both of those properties. Okay? NP completeness is one of the critical things. In fact, we have given the Nobel Prize for computer science, which is called the Turing Award, to one of our faculty on this department. We got the equivalent of a Turing Award for the task of taking all these problems that were actually separate and proving that you could reduce them all to each other. That was so cool that like solving one of them means it solves the whole group of them. And this was Richard Karp back, I believe, in the 70s, getting the Turing Award Prize for doing exactly this, saying these problems that are all different, no, they're all really the same. Isn't that cool? That's actually really cool. So, the fundamental question of computer science, the thing that you normally don't learn until you're a senior, we're trying to water down to CS10 level, which is P equal to NP? The class of problems that you can do in poly time, is that equal to the class of problems that are intractable? Are they really different? Is there a case? Is it just the case that we haven't found an efficient solution to the NP complete guys yet? Or we'll never find an efficient solution to these guys and they're different? If P is not equal to NP, then what you have is this picture on the right, which really helped me when I was learning this stuff, which is all the things that are NP problems, things you can verify in poly time, are here. Some of those are P problems. Some of those are NP complete problems. The rest of them are NP. Okay? So P is smaller than NP in that case because that's a subset of the whole things that are NP. NP complete is a subset of those hardest guys. NP complete is like the hardest carpets, right? The NP complete means the hardest carpets ever to kind of wash. Okay? P problems are like the easiest carpets. We can wash, come on, it's like a square, right? How hard is it to wash a square? Zoop, 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 I'm done with the square. Or rectangle. Ooh, rectangle. Still hard. No, easy, right? Okay. It's the angles and the hard stuff that makes things hard. The hardest ever, NP complete. Okay? By the way, here's the coolest part of the slide. This is the unsolved problem in the entire field of computer science. Grand unifying theory of physics, that's one of theirs. For us, it's just this. It's what P equals NP. That's all we care about. There's some small problems, but this is it. That's the big one. That's the granddaddy of all problems in computer science. It's really cool. And all it takes, guys, this is the coolest thing. All it takes is for somebody smart to prove that P equals NP. All it takes is somebody can wash the hardest carpets and find a solution to those hardest carpets in polynomial time. If you can solve any of the hardest category, this exalted NP complete group, you solve one of them. You solve any one, and you find a clever polynomial time solution, you've solved everyone in NP complete and everyone in NP. You've solved everybody in white there. That entire group of problems you've solved in polynomial time if you solve one guy in the red NP complete region. Isn't that cool? Don't you think that's really cool? You solve one, you solve everybody. So, and by the way, what are some of those problems that are in there? Cryptography problems. Like Department of Defense has data that's crucial to the United States and to lives. Someone solves it. They then go and break all the keys to all of your passwords. Because part of that involves it's an NP-complete problem to crack those passwords. But you solve one of those, you crack everyone's password. You guys get that? How big this is? It's a big deal. People are saying, well, look, we're trying to prove that, no, these are two separate things. P is not equal to NP. But how do you prove the two things aren't equal? All it takes is one example of a P-type solution for an NP-complete problem, and you've solved the whole thing. So how do you prove that you can never find that? That's a lot harder to prove, and they haven't proved it yet. Is that cool? Okay. Other NP-complete problems, by the way, are the traveling salesman problem, who needs the most efficient route to visit all the cities and come back home. You have to visit every city in my graph and come back home. So I have two fun comics. My hobby, embedding, and now you guys can get XKCD comics. See, you didn't get them before. Now you can get them, right? Watch. My hobby, embedding NP-complete problems in restaurant orders. So here's Chachi's restaurant, mixed fruit $2.15, French fries $2.75, side salad $2.35. And the conversation goes like this. We'd like exactly $15.05 worth of appetizers, please. Exactly. These problems on the knapsack problem might help you out. Because it's the knapsack problem, right? You guys get it's the knapsack problem he's trying to ask for, right? Listen, I have 6 other orders to get to. As fast as possible, of course. Do you want something on the traveling salesman? Because the traveling salesman is also NP-complete. You solve that one, you solve this one. Isn't that cool? Okay, this is the traveling salesman problem, which again is a problem of needing to visit every single city in the most efficient way. There's all these maps. You can take this map, this map, this map, and you need to visit the most efficiently. So the brute force solution is n factorial, which is a big number, right? Which is also intractable. Dynamic programming, which you'll learn later in CS, is order of n squared 2 to the n. Still better than n factorial, but still intractable, right? Selling on eBay, O of 1, which means constant, which you guys know what constant means, right? eBay, click, sold, right? No traveling at all. And the guy turns back to this salesman and says, still working on your route? Be quiet, okay? That's pretty funny. Okay, so now gets to some of the richest and coolest stuff with only 5 minutes left to go. Let's see if I can do this. And I won't rush through this. I'll push it to next time because this is so important. There are problems that are not solvable, period, okay? What do you mean not solvable? No, every problem's solvable. They used to think, this little bottom slide below, this is Alan Turing, by the way. Alan Turing, one of the earliest computer scientists, one of the most important people in the entire field, Alan Turing. Okay? By the way, zoop, Alan Turing was born about 100 years ago. So this is the Turing centennial. People are all across the world are celebrating Alan Turing's life and what the importance he's had to computer science. By the way, he almost single-handedly saved World War II for the good guys. Just to let you know. He cracked the Germans' code. It's pretty good enough, right? Okay? He cracked the German code, and you have to read about Alan Turing for next week because it's so important. He cracked the German code, and thanks to that, the good guys won. All right. Decision problems. Answer yes or no for an infinite number of inputs. Okay, so what does that mean? Here's an example of some decision problems. Is n prime? N is an infinite number, right? Is it prime or not? Well, that's easy. You try to divide it out and you figure it out. That's a decidable, a decision problem, and that's decidable, right? Is the sentence S grammatically correct? There's an infinite number of valid sentences. I can give you a generator that generates an infinite number of sentences, right? You can just say Bob and Sue and Joe and infinitely, right? So I can ask you this infinitely long sentence, this finite sentence, but it's an infinite number of those sentences that could be, finite sentence, is that grammatically correct? And you just follow the rules of English and see a little Chomsky diagram and see if it's valid, okay? An algorithm is a solution if it correctly answers yes or no in a finite amount of time. It has to be a solution, okay? Sorry, a solution has to answer yes or no and not go off into the corner and just spin, okay? Can't take forever to do it. Can't be forever. A problem is decidable if it has a solution, okay? Decidable if it has a solution. Solution says yes or no in a finite amount of time, and those are called decision problems. And Alan Turing was amazing. So let's review proof by contradiction. Proof by contradiction is a mathematical concept which I'm going to use on the next slide. Proof by contradiction says you assume, to prove something, you assume the opposite. Then you prove that that's impossible. Therefore, I've proved the original thing. For example, this is a beautiful example. To prove that there's a theory, I believe that there are an infinitely many number of prime numbers. Okay, how would you prove that? Let's prove by contradiction. First, let's assume there are a finite number of prime numbers. You put them in this room. You order them all. You list them from prime 1 to prime n. And now, everyone in this room, what's the product of you all? I multiply you all together, the pi of this whole set. Okay? I add 1 to that. That new number is bigger than everybody else, because you only get bigger when you multiply in positive numbers. That's A. B, any of those prime numbers divided by this new number q, is going to have a remainder of 1. Prime numbers 2, 3, and 5. Example, right? Let's say that 5 is the biggest one. 2 times 3, 6 times 5, 30. You add 1, 31. I'm telling you divide 31 by 2, remainder 1. 31 by 3, remainder 1. 31 by 5, remainder 1. You get remainder 1 divided by any of those primes. Therefore, it's prime, because you don't get an even divisor, right? You always have a remainder. Therefore, that new number is A, bigger than the other guys, and it proves that there's not a finite number, because I'm now gave you a new one that I guarantee is prime, given that proof, and is bigger than the other guys. So there is no biggest prime number. Proof by contradiction, right? I proved that there was no, you said assume that there's a biggest prime number. I proved that there was impossible to have a biggest prime number because I could generate a null then after that. That, by the way, is a convenient prime number generator, if you ever wanted to know that. Okay? So that's proof by contradiction. You ready? So now let me introduce the halting problem. The beginning of this is, I'm proving this why? Because Turing proved that it wasn't, not all problems are decidable. And decidability is whether you can answer yes or no in a finite amount of time. Okay? Everyone initially said, yeah, every problem is decidable. Come on. Is this number prime? Yes or no? I mean, anything is. How could you not have something that's decidable? Turing said, oh yeah? Watch me. So Turing, who turns 100, would have turned 100 this year, has the following proof. Okay, here's the following. He wants to be able to construct a function, a machine, that, given a program and its input, will tell if that program run on that input will eventually stop. That'd be useful, right? You have all your final projects, and you say, ready, go, and you run it, and it waits a long time, and a long time, and a long time. And you ask yourself, is it the case that if I ever just, you ever had the case where you're waiting in line for something and they never move, the line at the supermarket never moves? You're like, oh, geez. And the moment you switch lines, all of a sudden the line opens up and it goes really fast. You're like, if I had just stayed there, I would have been at a better deal than leaving. The whole thing. It happens all the time to me. I know, I remember it's like, what's the thing where it's always the worst? Murphy. Maybe it's Murphy on my back. It's always Murphy. It's always the line that I'm in is the slowest line. And the moment I just say, forget this line, I'll go home, all of a sudden, bleep, they all go first. And I would have just been there, okay? So it's useful to know whether, should I keep waiting for this thing or am I really stuck in a loop or not, right? It's really useful to know whether your piece of code is in a loop or not. Because if it's in a loop, you say, why am I waiting? It's in a loop. The program said it was in a loop. That's why this would be a useful program. So it's relevant, right? And useful. So that's the goal. The goal is, can we write a program which loads in your BYOB program, goes, hey, give me your BYOB program, bloop, and take in the input you want to run your BYOB program on, bloop, and it will tell you, oh, sorry, that's going to infinite loop. Or it'll tell you whether it's going to eventually stop or not. That's kind of useful, right? So he wants to say, the question is that decidable or not? That's the question. So this is he's going to use this as metal to prove that not all problems are decidable. Okay? So assume we could write this problem. Let's assume it's done. Hey, we've written this program. Assume we can write it. Because he wants to prove that you can't get this, that this cannot be ever written. He wants to prove, this is called the halting problem, that you want to write something that can find where the code will ever halt or not. So that's called the halting problem. And he wants to prove that you cannot ever have a halting problem piece of code. The top thing that he has, he says you can never have that. So that's not a decidable question. Let's see if we can follow that proof of why that's not decidable. Step number 1. Let's assume we could write it. Let's assume we have it. Yay, we have it. Okay? And the title of that, you see on the right, is Would the Program Stop on the Input? Okay, that's what it is. Here's what he's doing inside of it. If you peek inside, here's how he writes it. Okay? He says, and look how very easy it is. If something clever, imagine something clever is like a helper function. That's basically doing all the work for you, okay? If something clever returns true, then you say true. If something clever returns false, you say false. You see? And by the way, this shouldn't be a big idea because you know that a program or a function can be input. We know that for several weeks now. So program as an input, only you guys in CS10, and only you guys in the beauty and joy of computing who know and feel that it's no big deal to have programs and data be input, functions be input, can even get to this slide. The rest of the people who don't know that are like, what? Programs aren't input, and they're stuck on that first block. But that block is no big deal, right? That block is a block that you could write yourself. The key is something clever does all the hard work. Somebody writes something clever, and you basically report whatever something clever does. You got that? So that first block is not hard, right? You could write it yourself. I didn't tell you how to write something clever. Assume something clever does all the work for you. But remember, we're assuming this thing works. So now I can write another block, which the code is right here. The code is called stops on self. Stops on self. And that reports whether a program would stop if it were given itself as the input. Rather than, compute on this list of numbers, no, compute on this program itself. So program can be data. So would the program stop if you handed itself as the input? And there's the code for it. Look, report would program stop on program. That's not rocket science. Nothing there you haven't seen already. Okay? Let's assume that works. You say, why am I writing that? Watch this. Watch the key thing. Then, if that exists, so far I assume that the first one were true because that's our assumption. The yellow assumption you see is they assume that the top guy works. Would program stop on input? That exists for me. Because you write it here and something clever is the guy that does the majority of the work on it. Stops on self is the code right there. That's not hard. There's the code right in front of you. Here's the magic of the proof. It's so elegant and so beautiful. Let's write a function called weird. It takes input a program. Okay? Takes input a function, right? It takes input a program. Now, here's what it does. Let's look at the code. It says, if stops on self program returns true, then I am going to loop forever. I'll just spin forever. I'll never return. Okay? So call stops on self, which is the guy right above it. And if stops on self returns true, I'm going to loop forever. If it returns false, I'm going to return true. Okay? Weird. Now, what is the following block in the bottom left? What's weird called on weird? You know how to make something call in a function. You can do that. That's what map does. That's what reduce does, right? It takes a function as input. Weird takes in a program. So what program are you taking it in? Weird itself. Okay? So now here's the beauty of the proof. Watch the following. I ask you, does weird stop on itself? That's what I'm asking. So half of you are going to say true. You guys are far, all the sides, raise your hand if you're on the far side. On the far side, you're halfway, that right half? Okay. You guys are saying true, okay? Hey, does weird stop on itself? What do you say? True. All right, let's see it. Let's try it, okay? They said weird stops on itself. True, right? So let's try it. Weird stops on itself. Well, then what does weird do? Weird says, if stops on self program. Okay? So they told me weird does stop on itself. Then I asked it, if stops on self weird. What does stops on self weird return? True. So what do you do? What does that code do? What does weird return then? A forever loop. Wait. You're telling me that weird returns a forever loop. Weird called on weird returns a forever loop. Didn't you just say that weird stops on self return true, which means it will stop? But what happens in that code of weird? It runs forever. What's that called? A contradiction. You said it does stop on self, but I wrote you code that weird on itself does not stop on self. So that's impossible. So guess what? You guys are all wrong. Weird cannot stop on itself. So you guys are right, must be, right? Weird does not stop on itself. Weird loops on itself, okay? Are you with me? So now, let's try it now. You're telling me weird does not stop on itself. So, let's look at weird. What's weird of weird? Does weird stop on itself? What do you guys say? False. But wait, what does weird return then? True. Wait, you just said you returned false, and yet you also returned true. Contradiction. So, because of that beautiful case, I ask if you stop on yourself, you say you do. And then, guess what happens? You loop forever. Weird on weird loops forever. So you can't both stop on yourself and not stop on yourself. I said, do you return true or false? You said false, but then you also return true. That's a contradiction. So guess what? It's not that weird can't be written. There it is. It's not that stops on self can't be written. There it is. It's that would program stop on input can't be written because something clever is impossible. Therefore, this assumption, assume we could write it. The two options we had were both contradictions, a weird on weird. Therefore, we back up and we say what must be broken is something clever is impossible, which means would program stop on input is impossible. Therefore, you cannot write the halting problem. You cannot write that first bullet. It's uncalculable. It's not computable. Isn't that cool? Before he came up with it, they said, are all problems decidable? Everyone, the entire community said, yes, every problem is decidable. Until Turing, this brilliant man said, well, then how about this one? And then had this gorgeous, elegant proof that proved that that could never be written and is not decidable. So the halting problem is one example of a problem that is not decidable. So this whole lecture was about the different levels of complexity. Some things are tractable, some things are untractable, some things have approximations to them, some are not decidable at all. Isn't that cool? So, number one, complexity is a really important part of CS, certainly theoretical CS. If you're given a hard problem, rather than try to hit your head against the wall to solve it, look around and see if other people have solved it also. Maybe you can reduce your problem to their solution. It's kind of like if you try to figure something out, go to Google first to see if there's an answer. Same kind of idea, right? If you don't need an exact solution, consider an approximation. And that's, you also probably know that as well. But if you do need exact, sometimes those exact things are hard, okay?